Look at your hand. Seriously, look at it. Right now, it's being pulled toward the center of the earth with an incredible, relentless force. You can feel its weight. Now look at the phone in your other hand or imagine a feather, a book, a bowling ball, all being pulled down. And here is the lie you've lived with your entire life, the thing your eyes see every single day. You think the heavier thing falls faster. You know it. You've seen a rock plummet and a leaf flutter. Your entire intuition, your common sense, screams that gravity treats different objects differently. But what if I told you that's a complete illusion? That in the pure, silent vacuum of space, a feather and a battleship would hit the ground at the exact same moment? And not just hit the ground at the same time, but that this simple, bizarre fact is a crack in the floor of reality, a clue that what we call gravity isn't what we think it is at all. It's not a force pulling things down. It's something else entirely, something so strange that once you see it, the universe will never feel solid again. Your common sense is lying to you. Not because you're foolish, but because you're human, living in an atmosphere, on a messy planet full of air and friction. The universe, however, plays by cleaner, more elegant, and far weirder rules. The beautiful, shocking truth is that all objects, regardless of their mass, accelerate toward the Earth at exactly the same rate when only gravity is acting on them. 9.8 meters per second squared. A number you might remember from school, but probably never felt the strangeness of. This isn't a simplification for textbooks. This is a fundamental property of our universe, verified with stunning precision. It means the heaviness of an object, the gravitational pull it feels, and its laziness, its resistance to being moved, what we call inertia, are exactly, perfectly, mysteriously proportional. They are two sides of the same coin. Why? The universe doesn't have to work this way. It could have been different, but it's not. And this perfect balance, this cosmic coincidence, was the breadcrumb trail that led Einstein to completely rewrite our understanding of space, time, and reality itself. So if you're already questioning the ground beneath your feet literally, then you're exactly where you need to be. This is what we do here at Think Beyond Physics. We don't just repeat facts from a textbook. We dig into the why until the floor falls out from under our assumptions. We follow those breadcrumbs to the profound truths hiding in plain sight. So, if you want to see where this trail leads, if you're ready to have your common sense shattered and rebuilt on a deeper foundation, hit that subscribe button right now. Join a community that isn't satisfied with "that's just how it is." Because we're about to go on a journey, starting with a simple, falling apple, and ending at the edge of a black hole. And it all begins by understanding why, against all appearances, everything falls the same. So let's stare directly at this contradiction, this thing that feels so right and is so wrong. Think about dropping a marble and a cannonball from the same height. You don't even need to do the experiment. Your mind's eye already sees the cannonball winning. It's heavier, it wants to get to the ground more, right? Gravity pulls harder on it. That's the logic. And in the real world, with air whooshing past, the cannonball does hit first. The air pushes up on the light marble more, slowing it down. That part is true. But here's the first crack in the logic. If gravity pulls harder on the heavier object, why doesn't it absolutely zoom ahead? If I pull a child's wagon with all my strength, and I pull a freight train with that exact same strength, the wagon takes off and the train doesn't budge. The force is the same, but the results are wildly different because the train has so much more inertia it resists being moved. So for gravity, if it's just a pull, we have a puzzle. Yes, the Earth pulls harder on the cannonball. But the cannonball also has more inertia, more resistance to changing its motion. It's like the universe has two separate dials, one for gravitational pull and one for laziness. And our puzzle is this: in our world, these two dials are always, perfectly, locked together. Turn up the mass, and you turn up the pull and the laziness by precisely the same amount. They cancel each other out perfectly, leaving the acceleration, the rate of speeding up, identical. But wait, you might think, maybe it's a trick. Maybe for simple, solid objects, it works, but what about something crazy? What about a grain of sand versus the entire moon? Surely the Earth's gravity yanks the moon with unimaginable force. And it does. But the moon's inertia to being moved is also unimaginably huge. The two unimaginables balance perfectly. This isn't just theoretical. It's been tested. Not just with feathers and hammers on the airless moon, you've seen that footage, but in exquisite laboratory experiments on Earth. Scientists have measured the acceleration of different materials, different weights, with insane precision. And within the tiniest, most negligible margins of error, they fall at the same rate. The universe is insisting on this rule. Galileo is said to have dropped objects from the Leaning Tower of Pisa. Whether he actually did or not is less important than the thought experiment he proposed, which cuts through the noise of air. Imagine two objects tied together with a piece of string. According to the heavier is faster logic, the lighter one should slow down the heavier one when they're connected, like a parachute. So the combined, heavier object should fall slower than the heavy object alone. But that's nonsense. Tie a rock to a bigger rock, and you just have a heavier rock. Which is it? Does being heavier make you fall faster or slower? The logic of our common sense collapses on itself. This simple paradox tells us our starting assumption is broken. Something deep is going on. And to find it, we have to stop thinking of gravity as a force that pulls. We have to think of it as something that guides. Now, before we jump into the deep end, let's stay right here in the familiar for a moment. Because the secret isn't hiding in some exotic lab, it's in your daily life, if you know how to look. You feel gravity, right? You feel weight. When you're in an elevator that starts going up, you feel heavier for a second, pressed into the floor. When it starts going down, you feel lighter, almost floaty. That sensation is your body's inertia resisting the change in motion, and it feels identical to a change in gravity. But here's the key, it feels identical because, in a profound way, it is identical. Your body can't tell the difference between being at rest on Earth and feeling gravity's pull, and being in a rocket in deep space accelerating at 9.8 meters per second squared. In both cases, your feet press against the floor with the same force. This is a massive clue. Let's do a thought experiment. Imagine you're in a sealed, windowless box. You can do experiments inside. You drop a marble. It falls to the floor. You feel your own weight. Is the box sitting on the surface of the Earth? Or is it out in the emptiness of space, with a rocket engine attached to its bottom, accelerating at a steady 1 gravity? Can you tell? Can any experiment you do inside that box tell you the difference? If you drop two different objects, a feather and a hammer, what happens? On Earth, with air in the box, the feather flutters. But if you pump all the air out, creating a vacuum, they hit the bottom at exactly the same time. Now, in the rocket ship version, accelerating through space, you pump the air out and do the same thing. You let go of the feather and hammer. From your perspective inside the box, what do? Do they float? No, because the floor of the box is accelerating up to meet them. They appear to fall to the floor, and crucially they will hit at the same time. There is no air to slow the feather, and from the perspective inside the box, they are both just sitting there while the floor races up. Their inertia is the only thing that matters, and the floor hits them simultaneously. Inside your sealed box, you cannot tell. The two scenarios are perfectly equivalent. This is the core of Einstein's beautiful insight, called the equivalence principle. Gravity, in a local experiment, is indistinguishable from acceleration. The force of gravity you feel isn't really a force in the Newtonian sense of a pull. It's more like you're in that accelerating box all the time, and the Earth is the floor rushing up to meet you. But that's a weird picture. The Earth isn't moving up. So what's really accelerating? This is where we have to let go of our picture of a flat, static stage of space. Think of a trampoline. Place a heavy bowling ball in the center. The fabric stretches and curves. Now roll a marble near the edge. It will spiral and toward the bowling ball. From above, it looks like the marble is being pulled toward the center. But the marble isn't being pulled by a mysterious force. It's simply following the straightest possible path along the curved fabric. The curvature is the gravity. The Earth isn't pulling on the falling apple. The mass of the Earth has curved the space and time around it, and the apple is just following the natural, unforced geometry of that curved world line. It's going straight in a curved universe. And here's the breathtaking punchline for why all things fall the same. In this picture, the object's mass doesn't appear in the equation for its path. A feather, a cannonball, a planet, they are all just following the geometry. The cannonball has more mass, so it takes more force to deflect it from this natural path, right? That's our old inertia thinking. But in general relativity, there is no separate force to apply. The path is the natural path for all objects. The curvature of spacetime tells objects how to move, and the object's properties, except for their energy and momentum, which for slow-moving objects is tied to mass, don't change the shape of the stage. They're all just actors following the same stage directions written into the shape of the universe itself. So when you see something fall, you're not watching a force act. You're watching an object being utterly, completely, and freely loyal to the shape of reality. It has no choice, and neither does anything else. That's why they all do it together. So let's put the pieces together. We started with a simple, false fact: gravity pulls harder on heavier things. We saw that logic crumble because inertia balances it perfectly. We felt the equivalence between acceleration and gravity in an elevator, and we glimpsed the idea of a curved stage. Now let's connect these dots into the actual, stunning mechanism. You have to forget the idea of gravity as an invisible arm reaching out and yanking things. That's a useful story for calculations, but it's not what's happening. What's happening is that mass and energy, the stuff that makes up you, me, this planet, change the very shape of space and time around them. They create what we call a gravitational field. But a field of what? Not a force. A field of geometry. Imagine space is not an empty grid, but a quiet, stretchy substance. When there's no mass around, it's flat and even. Now put a planet into that substance. The substance stretches and warps, creating a valley. This isn't just a metaphor, this is the mathematics of general relativity. The planet makes a dent. Now, take another object, any object, and set it moving near this dent. What path will it take? If it's moving sideways, the curvature of the valley will bend its path, maybe into an orbit. If it's just sitting still at the edge of the valley, it will begin to slide down the slope toward the bottom. From above, it looks like it's being attracted. But from its own perspective, it's just doing the most natural thing possible, following the shape of the terrain. It is moving along what physicists call a geodesic, the straightest possible line in a curved geometry. On the curved surface of the Earth, a geodesic is a great circle route for airplanes. In the curved spacetime around Earth, a geodesic for a stationary object is a line that points toward the planet's center. The object isn't being pushed or pulled onto that line. That line is its natural state of motion. Now, why does this make all things fall at the same rate? Because the path to geodesic is determined solely by the shape of the valley, not by the properties of the object sliding down it. A bowling ball and a feather, placed at the same spot on the same curved hillside, will both roll down. Their speed at any point depends on the steepness of the hill and their starting point, not on their weight. The steepness is the curvature, created by the Earth's mass. The starting point is the height from which you drop them. That's it. Their own mass doesn't change the hill. In the mathematics, the object's mass cancels out completely. On one side of the equation, you have the gravitational force, which is proportional to the object's mass. On the other side, you have F equals ma, the acceleration, which is also proportional to the object's mass. Since the mass appears on both sides, you can divide it out. The resulting acceleration, 9.8 meters per square second, has no mass in it. It's a property of the location in the gravitational field, not a property of the falling thing. This is the real meaning of Galileo's famous apocryphal experiment. It's not that air resistance masks the truth. It's that air resistance is the only thing creating the illusion of difference. Remove that, and you see the pure geometry at work. The hammer and feather on the moon weren't just a cool demonstration of vacuum, they were a direct visualization of geodesic motion. They were both being guided by the moon's curvature of spacetime, and since they started together and the geometry was the same for both, they arrived together. Their journey was written into the landscape before they were even dropped. But let's go deeper for a second, because there's a subtlety here that's absolutely beautiful. You might object, but if a more massive object, like a star, falls into this valley, wouldn't it change the valley itself? Doesn't it have its own gravity? You're absolutely right. It does. A cannonball warps spacetime a tiny, tiny bit more than a feather does. So technically, in a super precise sense, they are not falling in identical fields. The cannonball is falling in a field made by the Earth plus its own tiny field. But here's the miracle of the mathematics. For the kind of falling we're talking about, objects near Earth, that extra effect is so infinitesimally small it makes no measurable difference. The rule holds because gravity is extraordinarily weak compared to other forces. The Earth's curve is the overwhelming factor. The falling object's own mass is essentially a passenger, not a driver, of the geometry in this scenario. It is still following a geodesic, it's just that its geodesic is in a spacetime very, very slightly adjusted by its own presence. But the key point remains: the reason for its motion is the shape of the stage, not a tugging force. And that shape guides all passengers equally, regardless of their size, as long as they don't distort the stage themselves. And that's the true, quiet revolution in understanding. Things fall not because they are forced to, but because they are free to follow the simplest path in a world that is bent. Now we get to the heart of the strangeness. We've replaced force with geometry. But what does that actually mean for the fabric of reality? To see it, we have to stop thinking of space and time as separate things. That's the real leap. You and I live in a world of 3 dimensions of space and 1 of time, and we treat them differently. We move through space, but time just happens to us. Einstein's genius was to stitch them together into a single, 4-dimensional fabric, spacetime. This isn't just philosophy. It has concrete, testable consequences. Mass and energy don't just bend space like a dent in a sheet. They bend spacetime. And that bending affects how objects move through space and how time itself flows. Let's make this tangible. Imagine our stretched fabric again, but now it's a block of clear, flexible gelatin that's spacetime. The vertical direction represents time, always flowing upward. When there's no mass, the gelatin is uniform. A path through it, the life history of a particle just floating in space, is a straight line upwards. It goes forward in time but doesn't move in space. That's being at rest. Now, embed a heavy mass of planet into the gelatin. It creates a curving, funnel-shaped warp. Now, take that straight, upward line of a floating particle and bring it near the warp. The line gets bent inward toward the mass. That bending of its world line is what we see as gravitational attraction. It's being drawn toward the mass in space because its path through time is being tilted by the curvature. Gravity, in this picture, is the tendency of world lines to converge toward regions of dense mass energy. It's not an action at a distance, it's a local feature of the path you're on. This explains the equivalence principle with devastating elegance. Remember the sealed box? The feeling of weight? In the spacetime picture, sitting on Earth means your world line is a curve being pushed upward through time against the fixed floor. That push is what you feel as weight. In the rocket accelerating in flat spacetime, your world line is also a curve, a hyperbolic path being pushed against the accelerating floor. In both cases, your world line is not a straight geodesic in the flat sense. You are being forced off your natural, geodesic path. In the gravitational case, your natural path is falling, but the ground is in the way, pushing you onto a curved, non-geodesic path. Your body feels that as a continuous push. The force is the reaction force from the ground preventing you from following the geodesic. The falling apple? It's the one following the geodesic, the straightest path in the curved gelatin. It feels no force. It is, in the most profound sense, weightless. Astronauts in orbit aren't weightless because there's no gravity, a terrible, common lie. They are weightless because they are in free fall, following a geodesic around the Earth. The shuttle and their bodies are on identical, parallel geodesic paths, so they float relative to each other. They are all just falling together, guided by the same curvature. This is where the universality of free fall becomes a mathematical certainty. The geodesic equation, the core formula of general relativity that describes these natural paths, does not contain the mass of the following particle. It only contains the metric, the mathematical description of the spacetime curvature created by the source mass. It says, given this shape, here's the straightest line. Period. The test object's properties are irrelevant. It could be made of lead, hydrogen, or light itself. In fact, this is our most precise test. Light, which has no rest mass, is also bent by gravity. Starlight curving around the sun during an eclipse proved Einstein right. Light follows a null geodesic, the straight line for massless things in curved spacetime. If the geometry guides even massless light, it must guide everything with the same impartiality. So let's connect this back to our cancelled masses. In Newton's view, the cancellation of inertial and gravitational mass was a miraculous coincidence. In Einstein's view, it's a necessary consequence of a deeper truth, what we call inertial mass, the m in F equals ma, and gravitational mass, the m in F equals gm1m2 / or superscript 2, aren't just numerically equal, they are the same thing. They are both a measure of an object's energy content, its ability to curve spacetime, and its resistance to having its path changed. They are two manifestations of a single property. An object doesn't follow a curved path because a force is acting on its gravitational mass. It follows that path because that's the straight line. And it would take a different kind of force, like a push from a rocket, to deflect it from that straight line, and the resistance to that deflection is its inertial mass. But in the language of curved spacetime, the path and the resistance are unified. The object's energy momentum tells spacetime how to curve, and that curved spacetime tells the object how to move. It's a self-consistent, elegant dialogue, not a one-way command. And this is why, when you do the Newtonian math, the m cancels out. Because it was never really two different m's to begin with. It was always just one m, wearing two different hats in an outdated play. We took the hats off and saw the actor underneath, an object simply being loyal to the shape of the universe. So what have we really uncovered? We started with a simple question about falling objects and ended up dismantling our most basic idea of force, space, and time. The mind-bending conclusion isn't just that things fall at the same rate. It's that they do so because nothing is pulling them. You are not glued to the earth by a force. You are constantly being pushed up by the ground, away from your natural state, which is free fall. The force you feel every second of your life is the force of resistance, the floor holding you up, preventing you from following the geodesic that leads to the Earth's center. Your true, unforced state is that of the skydiver before they pull the chute, or the astronaut orbiting peacefully. Weight is an illusion of constraint. The falling object is the one experiencing true, unadulterated motion. This completely inverts our intuition. This has staggering implications. It means the entire cosmos is a landscape of these geodesics. Planets don't orbit because the sun pulls on them. They orbit because the sun's mass has carved a curved valley in spacetime, and the planets are like marbles rolling around the rim. Their sideways motion keeps them in the curved path. They are, at every instant, falling toward the sun, but their speed means they keep missing it. It's a perpetual, elegant freefall. A black hole is simply a part of this landscape where the curvature becomes so extreme that all geodesics, even those of light, point inexorably inward. There is no mysterious sucking power. There is just a slope so steep that nothing can climb out. But the deepest philosophical implication is about the nature of reality itself. We think of the universe as a container, a stage within which things happen. Space is the stage, time is the clock, and matter are the actors. General relativity says no. The stage, the clock, and the actors are all part of the same dynamical, interactive entity, spacetime. Matter tells spacetime how to curve, curved spacetime tells matter how to move. They are inseparable. There is no fixed background. The geometry is physical, dynamic, and participatory. This shatters the common-sense notion of a passive, empty space. The falling of an object is not an event in space, it is the unraveling of a thread of spacetime itself. This brings us to a profound, almost humbling, realization about our place in the cosmos. The law that makes a feather and a planet fall the same way is not just a rule about gravity. It is a statement about the democracy of motion in the universe. The geometry does not play favorites. It does not care what you are made of, how big you are, or what you think. It provides a path, and all are equally free to follow it. The universe is not a collection of things being acted upon by forces. It is a tapestry of world lines, woven together by mutual interaction, each following its own straightest possible thread in a collectively curved fabric. Your world line, right now, is curved upward by the pressure of the chair beneath you. But the real you, the unforced, fundamental version, is the path you would take if that chair vanished. That path is written into the shape of the planet beneath your feet. You are, in that sense, already in motion. You are always falling. You are just being politely, and constantly, interrupted. This is the true meaning of thinking beyond physics. It's not about memorizing facts like G equals 9.8. It's about seeing that this number falls out of a relationship between you, the Earth, and the nature of a four-dimensional continuum. It's about understanding that the solid ground is an illusion of acceleration, and that the real, natural state of everything in the universe is a kind of graceful, geometric falling along the curves of reality. The next time you drop your keys, don't just see them falling. See them being utterly, completely loyal to the true shape of the world. They aren't being pulled down. They are being set free. So when you started this video, you probably thought gravity was a force that pulls, and that it pulls harder on heavier things. Now you know the truth. It's not a pull at all. It's the shape of reality itself, guiding everything along equal paths. The feather and the hammer, you and me, were all just following the straightest possible lines in a curved universe. But here's what really matters. This isn't just a fact about falling. It's a window into a cosmos that is interactive, dynamic, and deeply, strangely beautiful. Physics doesn't just give us answers, it teaches us that the world is more interconnected and wondrous than our senses ever suggest. Now, I'm genuinely curious. This idea turns so much on its head. What did it click for you? Was it the realization that you're constantly being pushed up, not pulled down? Or that astronauts are actually falling? Drop it in the comments below. Tell me the one thing that shifted for you today. And if you came up with a great way to explain this to a friend, share that too. Let's build a conversation around seeing the world this way. And if this changed how you see something as basic as dropping your keys, imagine what it could do for someone else. Share this video. Not just because it's cool, but because it's a gift of perspective. Send it to a friend and say, explain this. Why does a feather fall as fast as a hammer in a vacuum? Watch their common sense tangle itself up, and then watch them have that moment of clarity. That's a powerful thing to share. Because that's the real journey we're on here at Think Beyond Physics. We started with a simple question about falling objects and ended at the nature of spacetime. That's the magic. Not that we can calculate how fast something falls, but that we can understand why it falls that way. We can peer into the machinery of the cosmos and see not chaotic forces, but an elegant, geometric dance. And you're not just a spectator in this universe. Your very world line is part of that dance. Every second you feel your weight, you are feeling the shape of the earth curving the space and time around you. You are, in the most literal sense, touching the fabric of reality. Once you see that, you can't unsee it. The universe becomes a little more comprehensible and infinitely more wonderful. Keep looking. Keep questioning. I'm Think Beyond Physics, and I'll see you in the next one.